Okay, so this was where we had left on Friday. I mean, our main achievement was we were looking for this matrix element of the time evolution operator, and we had seen that we could write it as a summation over the paths. So we were just giving an amplitude to each path that you can imagine, connecting the initial point to the final point, and that amplitude is nothing but this expression over there with suitable normalization, and then summing over all the paths gave us the total amplitude to propagate from x prime, or for our particle to propagate from x prime to x. Now we just made an example of the free particle. Well, it's not such an exciting example, but nevertheless we had seen that I mean, we can calculate these path integrals, at least in simple cases, and also the result does actually match the exact result we obtained by other means. Now, today we will continue along that line and see how we can approximate it. Now, most of the time we won't be able to exactly evaluate this path integral, but we can do quite good approximations to that one. Now, one observation is that this path integral approach also allowed us how we can recover the classical limit, in the sense that if we set h bar to very small, or if you take the limit, formal limit that h bar goes to 0, the only path that will contribute to our path integral will be the one that satisfies this one. This is nothing but our classical path. So we kind of have the classical limit from this path integral formalism. Now, even if h bar is non-zero, we can say that in systems that are close to classical limit, the dominant contribution will still be the classical path. So we can just consider this expansion. So we can just write an arbitrary path to be the classical path plus some deviation from the classical path. Now, after we make this substitution, then we might be able to claim that only for small values of delta x we will have a significant contribution. Now, one method that we will be using will be the functional derivatives. Have you heard of functional derivatives before? No? Okay, functional methods. Now, basically, this thing we had written was actually nothing but such a summation. 1 over 2 xi minus 1 minus v of xi. Yeah, here we have a squared times epsilon. So basically, we can just consider taking the derivatives of the right-hand side with respect to, let's say, xi. And then if we take the derivative of the left-hand side with respect to xi, what we would obtain was, okay, let's say xj. This will be 1 over 2 well, the derivative here will give me xi minus 1 times twice times the derivative of xi minus 1 with respect to xj, which will be equal, and then we have the potential term minus sum over epsilon derivative of vxi with respect to xj. Which ones? Now we have the epsilons. And since we have the epsilons, we have the epsilon squared over here. And so this would be equal to sum over 1 over 2. Now 2's will cancel, let's say in the first term. M over epsilon, one of the epsilons will cancel. xi minus 1. Kronecker delta ij minus Kronecker delta I minus 1j. If you just make the summation, this will be equal to m over epsilon Now with the summation, m over epsilon xj minus 1 minus, well, instead of I will just put j plus 1, xj plus 1 minus xj. And this would be equal to m over epsilon divided by epsilon multiplied by epsilon. So these epsilons, they will cancel. You see the first term is nothing but dx by dt. Evaluate that t is equal to, let's say, j times epsilon, minus the other one is dx by dt. Evaluate that t is equal to j plus 1 times epsilon. And there's also the potential term. And this will be equal to minus m del squared x by del t squared in the continuous limit. So this is, we have the discrete one, we started with the discrete one, and now we take the derivatives, and at the end we again took the continuous limit. We would rather avoid this intermediate step, and we would rather just go from just use the continuous limits all the time. And to do that, now here what we used was, we used the fact that del xi by del xj is equal to Kronecker delta ij. This is what we use. And so after the summation sign, we could just take everything out of the summation sign, etc. Now this one, when we go to the continuum limit, it will be just the x. Remember, I is, we are basically using it as a time index. So we are just inserting, if you remember, we were inserting the identities at different times, and I is just the count of the marking at which time we are inserting these identities. So this we can just say xt, and j is just some other time, t prime. This we have to define as the Kronecker delta t minus t prime. Now one of the reasons, well, quite often if you go from the discrete to the continuous, you end up having the Kronecker deltas replaced by Dirac deltas. So the main reason is, well, the Kronecker delta under summation, it just gives me you 1, but Dirac delta under integration gives you 1. So that's the main reason why you have this transition. Now let's see if we can actually get this result, plus, of course, the potential term. Let's see what happened. Oh, we have the epsilon. Let's see, did we do everything correct? Okay, so here we have the 1 over epsilons. And so we divide it by epsilons. Here we have the difference, and yes, here we have the epsilons. And of course, we don't want, when we take the limit as epsilon goes to 0, we don't want something that goes to 0. So we just replace it by Dirac delta. So this is kind of, you can look at this expression over there as the definition of the derivative of one function with respect to another function. With respect to the same function at a different time, let's say. It just behaves, in most circumstances, it just behaves like an ordinary derivative. In the sense that, for example, if you would like to calculate the variation of s and s being a functional of x and its derivatives, this is nothing but the derivative of f with respect to x at some time times the variation of x, how much you change x. And of course you have to evaluate sum over all possible values of x, or of all possible values of t. So this is how you calculate the variations of functions. Well, the basic idea is since x, okay, before taking the continuous limit, so we know that s will be a function of all these xi's, I mean, independent of how many we have. So eventually we will have infinitely many xi's. So s is a function of the xi's. So the variation of s as you change the xi is nothing but the derivative of s with respect to each one of these xi's multiplied by the changes in these xi's. Well, you sum over all the i's. So you see, this one, before going to the continuous limit, is actually a function of all the xi's. The points through which your trajectory passes. And this you can define as, now here it's kind of ordinary derivative. Well, here in the summation you don't have the dt epsilon. I mean, dt corresponds to epsilon. You don't have the epsilon in the summation sign, but remember over here, the ordinary derivative already comes with the epsilon. So, yeah. So it's... Sorry? No, it's not the ordinary derivative. It's the functional derivative. It amounts to ordinary derivative of the Lagrangian. So we will see that. Now let's look at the variation of the action. We know, so this is how we define it. Let's first check whether we get this relationship. So you see, there we only consider the kinetic energy. So let's take the derivative of dt 1 over 2 m dx by dt squared. Derivative of this one with respect to x, let's say at t prime. This will be equal to dt 1 over 2 m del by the derivative with respect to t prime. Well, this functional derivative is here, it will be quite similar to ordinary derivative in the sense that this will be dt 1 over 2m twice dx by dt times the functional derivative of the ordinary derivative of x. Now, the functional derivative and ordinary derivative, they just change, you can just change their order. The 2's, they cancel, dt m dx by dt, d by dt of the functional derivative of x of t with respect to x of t prime. But this we had defined as the Dirac delta of t minus t prime. Now we can do integration by part. On the limits, the Dirac delta will be 0. So this is equal to minus dt m d squared x by dt squared times the Dirac delta t minus t prime. So we get our result minus m d squared x by dt squared no Dirac delta. So we basically recover our previous result. Minus m, the second derivative of x. Of course, with the obvious elimination of the epsilon. And the epsilon is eliminated when we replace the Kronecker delta by Dirac delta. Well, basically, we replace the Kronecker delta by epsilon by Dirac delta. In the limit as epsilon goes to 0. Now let's see. Here we had the path integral, which we could also write as dx e to the power I over h bar s of x. Now we know that the dominant contribution, that is in most cases, should be from the classical path. So we can just write x as the classical path plus the variation, and then Taylor expand this. Yeah, Taylor expand in the functional form. This will be s of x classical plus delta of x, which will be s x classical. This is nothing but the classical action. Do you remember where we also had the classical action? There was one place where we also had the classical action in our discussions about approximate methods. Yeah, WKB. Yeah, this is WKB. Plus, there's also the first correction. Yeah, if you remember WKB, we just considered an expansion in terms of h bar. The zeroth order term was the classical action. Then we had the next corrections, which were proportional to h bar. Well, the next term over here will be the quantum corrections. And we had already said that the quantum corrections, they basically should disappear when h bar goes to 0. So the next term is of the order of h bar, should be of the order of h bar. So that it just disappears when we take the limit. So let's continue. Questions? Okay. dt, derivative of s with respect to classical action, no, not the classical action, x of t, delta x of t, plus the second term, dt1, dt2, del squared s by del xt1, del xt2, delta x1, delta x at t1, delta x of t2, plus the other terms. Well, this is, by the way, if you just take these terms only, this is just a harmonic approximation. Well, by the way, this derivative you are evaluating at x is equal to x classical. And the classical path is defined in a way that this is the definition of the classical path. And just one more point, the classical path, you have to define it in such a way that x classical at 0 is equal to x prime, this is our initial point, x classical at the time t, this is equal to x, which is our final point. So these variations, delta x at 0 is equal to delta x at t, this is equal to 0. So we started with a path integral where we were summing over all the paths that were satisfying these conditions, these initial and boundary conditions. Then we just found the classical path, and we are looking for the quantum fluctuations around these classical paths, and those quantum fluctuations should be 0 at the boundaries. So basically all the x and x prime dependencies are in the classical path. And if you remember the the other terms will only receive some contributions if you have terms like x cubed in your Lagrangian. And those are absent in the harmonic oscillator. So these two terms, Sx is equal to S classical x, no, Sx classical, the action evaluated for the classical path, plus 1 over 2 dt1, dt2, delta x t1, derivative second variation of the action with respect to x at t1 and xt2, where x is equal to the classical path delta x t2 plus terms of the order of delta x cube. Well, let's see. This is still inside the path integral, but the first term is just a constant. It's independent of the path. So essentially, we have the x e to power minus I over h bar ht x prime. This is equal to e to power I over h bar times s x classical. This is also sometimes called the semi-classical approximation. Times sum over paths of e to power I over h bar 1 over 2 dt1 dt2 delta x t1 s x t1 delta x t2 delta x t2. Now there's a reason why I'm writing it in this form. Let's look at some multidimensional integral. Let's say that we are integrating over dx1, dx2 up to dxn. And we are taking the integral of e to power, let's say, minus xi, xj, aij. This will be equal to, now we will just show it, this is equal to square root of pi over determinant of A. Whatever that matrix A is. Can you see why? Sorry, pi to the n. Now pi to the n over 2 divided by square root of the determinant of A.
Square root, or is it also n over 2?
No, it's square root. No, not necessarily.
It's like Gaussian integral. The others are constants. Like they are integratable integrals.
True.
And then there's n over 2 products or something like
But for Gaussian,
The product of what? The product of what? You see, the Gaussian Aij should be diagonal, right? So it's not diagonal, but we can, okay, but can't we diagonalize it by a change of variables? Now you see, first of all, Aij is, we can write this xi, xj, Aij as x transpose Ax, where this x is such a row matrix. Secondly, A transpose is equal to A. That is, you can choose the matrix A such that A transpose is equal to A. Do you agree?
There should be a preference on I or J.
Well, in Aij, there is a preference. You see, you can just choose. You see, let's do an explicit example. Let's say we have n is just 2. We have x1 squared plus x1, x2 plus x2 squared. I can write this as, no, x2 squared. I can write this as x1, x2 1, 1, 1, x1, x2. This is one way of writing it. Or I can also write it as x1, x2, 1, 1, 1 over 2, 1 over 2, x1, x2. These two are the same. If we just multiply them out. So but still I can choose it to be symmetrical. That will always be possible. Now to see that xi, xj, aij, remember these ij's are dummy indices, so I can just change their name. So this is equal to xj, xi, aji. I just renamed them. I just called ij and I called ji. But you see, xj, xi, that is the same thing as xi, xj, aji. Now I just exchange the positions of xi, xj in the second step. But this just means that I can write this term over here as 1 over 2 xi, xj, aij plus xi, xj, aij. This is equal, no, ij. But I have one term, I divide it into two. Sum it twice and divide it into two. The first one is xi, xj, aij. It just stays there. For the second one, I can just use this one, which will be xi, xj, aji. This is equal to 1 over 2 xi, xj, aij plus aji. So even if you choose A to be not symmetrical, instead of A, I can just use A plus A transpose over 2. It will give me the same result. And A plus A transpose over 2 is a symmetrical matrix. And just like any symmetrical matrix, we can diagonalize our matrix A using an orthogonal transformation. So this, if I define Y to be some orthogonal matrix times X, such that this matrix M is equal, will be the transpose of this orthogonal matrix times some diagonal matrix times O. So I can just diagonalize A, find this matrix O, and then make a change of variable to Y. dx1 up to dxn will be just dy1 times dyn times the Jacobian of this transformation. And the Jacobian will be nothing but the determinant of O inverse. But being an orthogonal matrix, the determinant of O and its inverse, which is nothing but its transpose, it is just 1. Some linear algebra. And so what we have is, although initially we had this one, now we have the integral over the y's minus yi squared lambda I squared. Now lambda I, the eigenvalues of A. Now each one of these y integrals are independent of each other, and since each one is independent of each other, each one is a Gaussian integral, which just brings some product over I from 1 to n of square root of pi over lambda I. But the product of lambda i's is nothing but the determinant of the corresponding matrix. And the determinant is independent of whether you make an orthogonal transformation or not. The product of lambda i's is the determinant of D, but the determinant of D is nothing but determinant of A. So that's why if you have such a matrix, such an integral, this is equal to pi to the power n over 2 divided by square root of determinant of A. Now let's see, let's go. Now, any questions on this derivation? So it's just multi-dimensional integrations. A is a symmetric matrix. Well,
Is there any condition for this integral? Is there any condition for this integral? X1, x2 should be independent always.
well, since you are integrating over them independently, xi's are independent of each other. Well, the condition is the eigenvalue should be positive. That's probably the only condition. If they are negative, the eigenvalues, then it doesn't converge. You are integrating e to the power some positive number times y squared, you see here. If lambda I, if any one of those lambda i's is a negative number, so you are just integrating the exponentially increasing Gauss function. So that doesn't converge. There is problem with lambda i's being zeros. There are such cases when you will see that the lambda i's will be zeros, but in those cases, it mainly corresponds to some translational symmetry. It is infinite, but just like in the partition function, this path integral is nothing like it's just your partition function. So if you just multiply your partition function with some number, well, nothing really changes, because most of the time when you are calculating matrix elements, you will be dividing by your partition function anyway. So if you have, let's say, one of the so-called zero modes, if they exist, they just bring in an overall constant, although it is infinite. And in the matrix elements, again, it doesn't matter. It just cancels. But we will not be studying such cases. For example, I will not be using this one to evaluate the free particle path integral. It has a zero mode. It's possible that it has zero energy. So that's not, I will not use that here. So let's go back. We said that, okay, this was our approximate path integral. So this is nothing but e to the power I over h bar as x classical. Let's ignore some overall constant. Let me just write an n over here. This constant n also contains all the numbers we have, the overall factors in the definition of our measure, divided by square root of the determinant of this operator. Let's see what that operator is. Up to now, we were kind of leaving everything arbitrary. Now let's just calculate that operator. Now let's take the S to be dt 1 over 2 m dx by dt squared minus v of x del x by del x, let's say t2. This was equal to, well, the derivative of the first term, we had already evaluated it, and it was minus m d squared x by dt squared, and minus dt. Now let's take the derivative of v with respect to x of t. This is the ordinary derivative, by the way, times the functional derivative of x of t with respect to x of t2. This is equal to minus m d squared x by dt squared plus del v by del x. Now this is at t is equal to t2. Now everything is at t is equal to t2. By the way, this is your classical equation of motion. If you have a particle in a potential v, so the mass times the acceleration is equal to the force, which is minus the derivative of the potential with respect to the coordinate. So x classical just satisfies this is equal to 0. Now let's take the second derivative. This is equal to minus m d squared by dt squared Dirac delta t1 minus t2 plus the second derivative of v with respect to x, again Dirac delta t1 minus t2. This thing evaluate that x, no. Well, this basically tells us that it is a diagonal matrix. Dirac delta t1 minus t2 tells me that it's diagonal. So we need to go ahead and calculate the eigenvalues of this operator over there and multiply its eigenvalues, if we can. Yeah, it looks weird, but that's formally how you do it. Well, it's an operator, and you just write it in. You can write it in you can just choose a basis and write it in that basis. Try to evaluate its eigenvalues and multiply them, and that would give you the determinant. There are other methods of obtaining the determinants of operators. I mean, these are not matrices. I mean, you don't usually write these in terms of matrices, but you can still calculate these determinants. Now let us do it for the harmonic oscillator. Now for the harmonic oscillator, this will be exact anyway. So let's start with S is equal to dt 1 over 2 m x dot squared plus 1 over 2 m omega squared x squared. Now rather than using this expansion, and we can just evaluate it explicitly, just replace x with x classical plus delta x. 1 over 2 m x dot plus delta x dot squared plus 1 over 2 m omega squared x classical plus delta x squared. I have the classical action. You just take the x dot classical squared from the first term and x classical squared from the second term. That gives you the classical action. Plus, let's take the terms that are linear in the classical action. So this will be m delta x dot minus m omega squared delta x x classical dot m delta x times x classical plus dt 1 over 2 m delta x dot squared minus 1 over 2 m omega squared delta x squared. Now I will do some integration by parts. I will do integration by part in this term, and I will also do an integration by part in this term, in both of those terms. In the boundary delta x, we just said that it's just 0, so the boundaries will not contribute. So this will be S classical minus dt m x classical double dot plus m omega squared x classical times delta x. This is that first integral in the first line. Plus dt delta x of t 1 over 2 m d squared by dt squared minus 1 over 2 m omega squared delta x of t. Now this is nothing but I would say the second derivative, but there is a fact. Oh, okay. Let me also take these factors 2 out, 1 over 2. So this is 0 because we already chose the x classical to satisfy that equation. X classical double dot plus omega squared x classical is 0. Now if you look at this operator over here, that is nothing but this operator over here. So it's the second derivative. Well, here we have a Dirac delta, but remember we have two integrations over time. Over T1 and T2, using that Dirac delta, we can just integrate over one of the unknowns. So one of the times, so we are left with a single time integral, and this is what we have over here. And now the only thing left is to evaluate the determinant of this matrix. Or let's discretize it. That way it will be easier to see. So let's look at this one. dt Dirac delta x of t minus m d squared by dt squared minus m omega squared delta x of t. Now let me just write these, define these as y of t. Now I just don't want to write delta delta all the time. Y satisfies 0 on the boundaries of time. So this is nothing but sum over I times yi minus m. Well, there are various ways of writing these, the second derivative of the y, but let me just write it in this form. Sum over epsilon yi minus 1 divided by epsilon minus yi minus 1 minus yi minus 2 divided by epsilon. Everything over epsilon. Minus m omega squared yi. So this will be equal to sum over all I yi aij yj. Now what is this aij? It is epsilon minus m over epsilon Kronecker delta ij, the first one, minus Kronecker delta I minus 1 j divided by epsilon minus Kronecker delta I minus 1 j minus Kronecker delta I minus 2. Well, let me just change it slightly. I will say this is I plus 1, this is I. Again, this is I minus 1. In the limit, if we can take the exact limit as epsilon goes to 0, this shouldn't make any difference. Now this will give a more symmetrical matrix I. This is I plus 1 j I j minus Kronecker delta I j minus Kronecker delta I minus 1 j over epsilon minus m omega squared Kronecker delta I j. This is our matrix Aij. Well, you see, there are only three kinds of matrix Ij's for which these matrix elements are non-zero. The diagonal ones are non-zero. Aii, this is equal to epsilon, m over epsilon squared from the first term, and 2m over epsilon squared from the first term, and from the last one we have minus m omega squared. There is no sum over I. Are you familiar with Einstein's summation convention? So you see, when, for example, in the previous example, when I wrote xi, xj, aij, there is actually a sum over I and sum over j. So here there's I, the indices are repeated twice, but there is no sum over I. Ai, if j is I plus 1, then this is, we receive a contribution only from this term over here. This is epsilon times minus m over epsilon squared. And Aij minus 1, I receive a contribution only from this one. Now this is basically the same thing. Epsilon minus m over epsilon squared. So A matrix is a matrix of this form. The diagonals, you see all the diagonals are equal. Only the row just above and below the diagonals are non-zero, and they're also all equal. So basically, my matrix is like this. I have, let's say, A is on the diagonals, B is just above the diagonal, and B just below the diagonal. And 0 everywhere else. Now, what is the determinant of this one? And remember, this is an n minus 1 by n minus 1 matrix. Now, this is not a block diagonal matrix. You see, if it was just a 2 by 2 matrix, then it would be a squared minus b squared. If it was a block diagonal matrix of 2 by 2 matrices, then it would be a squared minus b squared raised to the power of the number of blocks. But this is not block diagonal. Well, let's see. Do you know how to calculate the determinant of a matrix? In general, not 2 by 2 or 3 by 3 matrices, but an arbitrary matrix.
The sum for I.
Hmm?
The sum. So the minus 1 to the I plus 2.
Kind of. Let's see. Let me just call the determinant of A to be n minus 1. Now, n minus 1 is just a dimension. So that's why I'm calling it n minus 1. Now, Bn minus 1, this is equal to A times Bn minus 2. Do you see why? Minus B squared times Bn minus 3. You see, if you have any matrix, A11, A12, A21, A22, now the determinant of this one is A11 times the determinant of, well, just eliminate the row and the column, A22 minus A12, determinant of, again, eliminate the row and the column of A12 this time. So this is A21 plus etc. So this is the origin of this first term. So I just take this A on the above left. What remains is an n minus 2, n minus 2 matrix of exactly the same form. Then the second term is B. Now when I eliminate the row and the column corresponding to that one, that's the first row and the second column, what remains is a matrix whose first row is a B at the top and 0 everywhere else. So I use that row to write down the determinant again. But that brings another factor of B, and I have lowered the dimensions of my matrix to n minus 3.
But then there is the third column. You see.
Well, let's see. Let's write it explicitly then. This is what we are trying to calculate. So this is equal to B n minus 1. This is equal to A times the determinant of AB, or A's, B's, zeros here, B, but this time this is done n minus 2 times n minus 2. Minus B times determinant of the third column is 0. So if we remove the second row and the second column and the second row, the first row, we have B, B. This is 0. This is A here, 0 here, 0 here. No, this is B. This is B. Okay. Now, to use this expansion that I wrote over here, you can either use any given row or any given column. You can do the same expansion for a column. Now, at this time, I'm using that one. I'm calculating the determinant of this thing with respect to this row, this column. But that would be B times the determinant of A, B, B, A, B, B, zeros, zeros, zeros all around. Now, this is an n minus 2 times n minus 2. So what remains is an n minus 3 times n minus 3 matrix. So I end up having the determinant of an n minus 1 and n minus 1 matrix. This is equal to A times the determinant of n minus 2, n minus 2 matrix of the same form, minus B squared times the determinant of n minus 3, n minus 3 matrix. So now I have a recursion formula. Well, of course, I need to start with knowing some of these. So let's calculate B2 AABB. This is equal to A squared minus B squared. And B1 is basically A. This is just A. Okay, now how can we solve this recursion formula? Okay. Okay, how shall we proceed? Mm-hmm.
Replace it, then we have R to the plus A R to the n minus 1 minus B squared R to the n minus squared. Solve for R. And we have two elements there. Then we have some.
Boundary conditions. We also have the boundary conditions.
Yeah.
Do you agree? No? Well, let's do one more trick. I mean, if we had such a recursion formula, Cn minus 1 is equal to R times Cn, then it will be kind of, no, n minus 2. Then it will be kind of trivial to solve it, right? This would be equal to R squared times Cn minus 3. This will be equal to R to the n minus 2 times C1. Then it would have been trivial. Well, we don't have this such a simple recursion formula because every b depends on the previous one and also the two previous one. But we can actually write it in such a form. So let's try to write it in such a form. I want bn minus 1. Let's just try to rewrite this, exactly the same expression. Bn minus 1, Bn minus 2. This is equal to some matrix, K, L, M, N. Bn minus 2, Bn minus 3. Because if we can do this one, then kind of we only need to take the suitable power of that KLMN matrix to relate the final expression, final result to our initial conditions. It will basically amount to what your friend was saying. Then to take the nth power, we will just diagonalize it, etc. So what should be this KLMN? Yeah, well, the trivial one, 1, 0, an minus b squared. The first line is nothing but our equation over there. And the second line just gives me bn minus 2 is equal to bn minus 2, which is trivially true. What are the eigenvalues of this equation? Well, let's see. Then this would be equal to a minus b squared 1, 0 raised to the power n minus 2, n minus 3, B2, B1. We already know what B2 and B1 are. Well, the easiest way to determine what should be this power is that power plus the subscript of the upper B, B2 is just n minus 1 all the time. How do you take the n minus third power of this matrix? Yeah, we will be diagonalizing it. So how do we diagonalize it? Yeah. Okay, do you see an easier way? Let's take its square. Maybe it will be proportional to identity or something like that. This is equal to a squared minus b squared, right? Yes. Minus ab squared, a and minus b squared. No. Okay. It's not easy. So let's diagonalize it. A minus lambda minus b squared, 1 minus lambda. Determinant of this one, this should be equal to 0. This is equal to lambda squared minus a squared plus b squared. Not a squared, lambda a. This should be equal to 0. Lambda is equal to a plus or minus square root of a squared minus 4b squared divided by 2. Well, let's continue after the break.